So, today we are doing a kind of post-solvable lesson. It's essentially going to be on Lee's theorem. Lee's theorem onto groups. I guess on would be less misleading. So recall a group G is solvable if it is a finite sequence of extensions of abelian groups. We define the derived series of G. They don't call it that here, but that's what it is. Gn of G, as you know it, G of 1 is G. G of n plus 1 is the commutator subgroup of Gn with itself. Thus, solvability of G is, as you'd expect, equivalent to saying that the nth derived series of G is equal to 1, I guess 1 as a group, for some finite n. Now here we're going to let G be a topological group, and a symbol which looks like, I'm going to just call it rho here, from G to the general linear Lie group of V. So this is like isomorphisms, and this is automorphisms, not endomorphisms. This is going to be a continuous homomorphism of G into, keep in mind that general linear Lie group is a group of automorphisms. Of a finite dimensional vector space V over, and in this case we're having it over the complex numbers. Theorem. If G is solvable and connected, there exists a flag f in V, which, keep in mind, is just like a series of subspaces, each contain the next, which goes up and down by a dimension at a time. This flag is invariant by our row of x for all x in G. We see the row is irreducible if v is not 0 and v and 0 this is kind of a definition inner proof are the only subspaces of V. This is not a proof, after all. The problem is I'm reading this as I'm writing it. Row, the subspaces of V, invariant by row x for all x in G. And before we prove the theorem, we have a couple corollaries of the theorem. First off, if G is solvable and connected, and rho is irreducible, sorry, I got distracted. If rho is irreducible, then the dimension of V is just 1. And by induction on dimension V, we get another corollary. It states that a compact, solvable, connected topological group is abelian. Now, by the Peter-Weil theorem, which I don't know if I've seen before, for any compact group G, there exists a family of irreducible representations rho alpha from G to the general linear Lie group of V alpha. Keep in mind this is how representations on groups work, it just has to be sending them to automorphisms such that the map from G to the product of these general linearly groups is injective. If for all alpha, the dimension of V alpha equals 1, then G is abelian. That is our proof of this corollary, I believe, maybe, potentially. Now, some terminology. element V in our vector space being acted on is an eigenvector for a subgroup H and G if it is non-zero and of course HV the image, the action of H on our V is just scaling V by some complex value for all H in our subgroup. Okay. An eigenvector V for H defines a character. I've heard about characters. Chi V sending H to, I believe this is the multiplicative group of the complex numbers, such that rho of H, the action of rho of H on V is equal to chi V of H on V for all H in H. So essentially we see here that by definition an eigenvector scales under the action of a subgroup, and chi, our character of that eigenvector, just states what the associated eigenvalue of any element of the subgroup is. Now, chi V is continuous as rho is the number of distinct characters of H Sorry, 1 second. Arising from eigenvectors of in our linear in our vector space is finite and is bounded by the dimension of our vector space. So we suppose that Vi from 1 to R is a maximal independent set of eigenvectors for H and V with characters chi I from 1 to R. Thus, if V is an eigenvector, I guess I can't abbreviate eigenvector in that way because it's an ambiguous eigenvalue. with character chi, we have that V is the sum of the eigenvectors with coefficients AI, with each AI being a complex number, and we obviously have that AI of chi of H is equal to AI of chi of H, chi I of H for each I. Hence chi is equal to chi I for some I. It can't be 0 as V can't be 0 because we define an eigenvalue as being non-zero. Now this is what they call the main lemma. Suppose G is connected. Let V be an eigenvector of a normal subgroup H. Then chi V of the conjugate of H by X is equal to chi V of H for all X in G, H in H. By computation, chi V of X inverse HX is equal to chi X V of H from above. H has finite characters of the form this is our proof of this, of the form chi xv for X in G. Hence, the subgroup S being X and G such that chi of xv is equal to chi of v is of finite index in G. S is closed in G though. G being the set of common zeros continuous functions of the form x to chi v of the conjugate of h by x minus chi v of h, as h ranges over big H. The decomposition of G into cosets of H, S, sorry, not H, this is expressing G as the disjoint union of finite non-empty closed sets. But we know that G is connected. S must be G. There can only be one such coset, which means for all x and g, chi x v is chi v. Alright. Proof of the theorem. Proof of the first theorem. We go by induction. On the smallest n, such that the nth derived series group of G is 1. Once again, the base case is not worth mentioning. If n is 1, then G1 equals G equals 1. And we're done. Because keep in mind, we're trying to show that there's a flag f and v, which is invariant by that every solvable connected group with a continuous representation has a flag in the vector space in which it acts, which is invariant by that representation for all x. If G is 1, it can only ever map to the identity of the general linear, and so we get everything we want. So, suppose n was greater than 1, so G2 does not equal G1, which is G. This is here by induction. We can suppose the theorem for G2 as it is connected. Let C be the set of commutators in G. It is connected as, not is, as the image of G times G under X times Y getting sent to the commutator of X and Y. X, Y, X inverse, Y inverse. Let Cm denote the elements of G which can be expressed as the products of M elements in C. I don't think this is going to be a subgroup for the obvious reason. Now the set Cm is connected as the continuous image of the product of a whole bunch of copies of C. And since U in C implies, I should draw that arrow better, implies that the inverse of U is in C. The subgroup of hang on, they wrote it weird, I gotta translate. The subgroup of G2 generated by C is the union of connected sets C to the M and C is connected as one is in the intersection of each Cm. By induction, there exists an eigenvalue vector. Why do I always want to say value when it's an eigenvector? V0 for G2 in V. We're going to let the function chi0 from G2 to C star be its character. By the main lemma, the set, I did not even write the words the, the set. I wonder, will this work? No, that doesn't do anything. The set of v in our vector space such that v behaves well with the character of v0 of v0 for all h in G2 is invariant under rho G. Now, let's suppose that rho is irreducible. Then rho of h acting on v is equal to chi of h acting on v, chi of h scaling v for all v in v and h in G2. Now we're going to let x in G, let h in G be the subgroup generated by x and G2. This is the subgroup of G. Since H contains G2, H is normal in G. Since, and this is where this comes into play, since C is algebraically closed, exists an eigenvector v1 for the operator generated by x under rho. From above, v from above v1 is then an eigenvector of G2 and hence, as it is for x by assumption, it is for all of h. So we're going to let chi1 from h to the multiplicative group of C be its character. By the main lemma again, we have that the set of v in v such that rho of h acting on v is that essentially V behaves with the character generated by representation of H in the way you would hope, generated by V1, sorry. All for all H in H is invariant under row of G and hence is just all of V. Thus, we have that row of X acting on V is an element of CV for all V in V. Since X is arbitrary, dimension of V is just 1. This is the direct proof, and I think it provides some good insight, but we have additionally a remark that Lee's theorem on groups and on algebras imply each other. Given this group statement, we get the algebra version in the case that our base ring is the complex field. By considering the connected Lie group of a given Lie algebra. In the case of arbitrary algebraically closed K, with, of course, the character of K being 0, is by the Lefschetz principle, which I certainly have never heard of before. So let's take a finitely generated subfield K prime of K containing the structure constants of G. I will go over what that is in a second. Because I think I skipped over those. And for the action of G and on V, embed K prime in C. Then descend from C to the image of K prime. And side note, for a basis EI of a Lie algebra, the structure constants are constant C, I, J, K, such that the bracket of any EI and EJ is the sum of all C, I, J, K, E, K. For across our n elements of the basis. Conversely, we can get the group version from the algebraic version by considering the closure of rho of G in the general linear Lie group of V as a real Lie group and applying the theorem to the algebra. I believe that's the end of our discussion on that. Yep. Next time we're going to the semi-simple case. I'm probably from the same book as always, but I am going to cross-check them once again beforehand, very briefly, what I can do here. And yeah, that'll be tomorrow, I guess.